Thank you very much. So, yeah, we're going to be looking at building Rock SOLID Serverless applications. So we're going to start with a classic example, a very simple application. And this is a blog application. And it's just a web app or an app service running on a server. It's connected to the database. We have authors and readers that connect to this app. And it's all just nice and simple. It's what we're sort of fairly used to. Okay, so then now, what happens when things go wrong? Our authors can't get to the app. Our readers can't read the content. We can't access the database. And we're questioning what's the end user experience like. We really don't know what's going on anymore. So we want to take this sort of a simple application, turn it into a serverless application, and then see how can we sort of deal with all these crazy things that go on and make sure our application is always available and always ready to use. So my name's William Liebenberg. I'm a solution architect here at SSW in Melbourne. You can find me on Twitter. I have a blog site called azuregems.io. And if you want to engage me a bit more formally, I'm also available on LinkedIn. I started coding about 5 years ago, when I was 5 years old, on a Spectre Video SV328. Now, this had a whopping 8 kilobytes of memory. And this is long before the internet and CD-ROMs, high volume storage. All our games and bits of code that we wrote had to be loaded from cassette tapes. So, a small program would have to fit into that 8 kilobytes worth of memory. And it had some really cool things back then. Yeah, a lot of good memories. Everything was quite beige back then. I think it's quite a lot better now. Interestingly enough, there's a project you can find on GitHub where someone has written a Spectre Video emulator or ZX Spectrum emulator running on Blazor. So those old games and things that we have, we can resurrect them and play them in the browser now. It's pretty cool. I started programming professionally in 2004 with C++. And then, the IDEs back then are fairly low res compared to today, but we still felt like we can take on the world and solve all their problems. Then around 2006, I jumped onto .NET 2. I skipped version 1 because I was pretty much stuck in my C++ ways and thought, what's this crazy new stuff? I don't want garbage collection. But I got convinced pretty quickly. I jumped onto .NET version 2, and I've been using it ever since. And now we've got .NET 5, and it's really, really awesome. For many years, I was working on industrial training simulations, especially with virtual reality. And I was lucky enough to get one of the very first Oculus Rift dev kits in Australia, sort of to try and set new standards for that industry. And then Azure came along. About 2014, I started working with Azure. And pretty much a day doesn't go by now where I don't do something in Azure. It's really big. There's a lot of services in there. So there's something in there for everyone, and every solution can make use of Azure. So today we're going to just look at a small slice of what we can grab out of Azure. So we're going to start off with explaining what is clean code and the solid principles. Then I move on to see how do we take those solid principles and apply them to a serverless application. Now, once we have that, we want to remove all that brittleness from our application. When things go wrong, what can we do? And once we've solved that problem, we want to see now how can we scale out our application. When we have high demand, we want to make it perform, and we want to be able to satisfy every request that comes into our application. So, clean code and solid. Why do we want to write clean code? Well, I think lots of us, most of us, would have been in a scenario where we look at the code quality measurements at the WTFs per minute. So good code would have a low rate, bad code would have quite a high rate, sometimes a very extreme rate. So for me, there's a lot of this comes down to two different types of coders that are out there. There's the duct tape coder that can come in and quickly just sticky tape a solution together, ship it, it works, and leave a trail of technical debt behind them, and sort of never come around to repaying that debt. And eventually, the application or the improvement starts to slow down. You have to walk through mud to sort of get things done, and it's not how you really want to have your projects to evolve. On the other hand, we've got the architectural astronauts where they can talk about architecture all day long, all the best solutions all day long. They're very expensive, but you can hardly ever get them to write any code. They don't always produce much. So for me, being somewhere in the middle is ideal, where I can go and write, simple solutions that work. They're easy to understand. You can look at the architecture and go, hey, I know what that does. It looks quite good. Don't see any problems. And that's great. So that's what we're going to try and aim to achieve with following clean code. So everything in clean code for me falls in the two main categories. Code should be easy to understand and easy to change. So whether it's my original code or if it's someone else that wrote the code, when I look at the code, the execution flow, it should read like a book. Anyone should be able to understand it. Look at the classes, the way that they interact, the functions and variables inside of them. Everything must have a purpose. It must be very clear and easy to understand and honest. If it says, say that's a name variable, it must be a name rather than a street address. So those things are very important and it must be easy to understand. So when it comes to changing the code or to maintain the code, you only need to change the code for one reason. Everything in there should be testable, and then if you've made a change that is a breaking change, you'll have some feedback to say, hey, this doesn't quite fit with what needs to happen, or the test is wrong. So you need to have all that feedback, and it just helps keep your code nice and maintainable. So you don't want to ship any known bugs. Now, a lot of the clean code principles have developed over about 30 years. Now, SOLID, so the acronym of acronyms, takes a whole bunch of different principles and puts them together. And this is how we get the word SOLID. So single responsibility, open closed, list cost substitution, interface segregation, and dependency inversion. So Uncle Bob, he's got a really nice book called Clean Code. So if you're not fully familiar with all the SOLID principles, don't worry, you can check out the book. There's a lot of sources online, or I'm going to cover all of these tonight as well. But the side effect of clean code is that you actually have a lot of files to deal with, and you need to arrange those files in some way. This is where clean architecture comes in, and it helps you to structure your application so that it's independent of other frameworks. Everything inside should be testable, like we mentioned earlier. It's independent of the UI framework. So if we, for instance, started off with an Angular application, and next year we're all going to be writing Blazor applications, so I should be able to replace Angular with Blazor without changing the core of the application. So the application and the domain layers there should be totally unaffected. And again, independent of a database. If we want, generally people start off with a SQL solution, maybe then realizing we can actually get more benefits from running a NoSQL Cosmos DB solution. So we should be able to swap that out and bring in Cosmos without changing the core of the application. And all of this is because the dependencies point inwards. We don't need to change the core of the application just because something on the outside has been changed. So this is quite nice. Now, Jason Taylor has a really awesome .NET CLI tool to generate a clean architecture solution for you. So you can check it out on that link there. And if you want some more nicer rules spelled out for you about clean architecture, we have a link there on SSW rules to clean architecture. So if you want to check that out, there's a lot of good info there. All right. So I know what clean code is. We've seen the SOLID principles. How are we going to take them and apply that to our serverless application? But why serverless, and what is serverless? Well, of course, there has to be a server somewhere. It's just that that's all hidden from us. So in our classic example, we are responsible for that server that runs our blog application. And when it goes down, we know about it. But in the serverless world, for instance, if that server goes down, Microsoft will, or whoever the cloud provider is, they will swap that out and bring another one in for you, and you're none the wiser. You just don't have to deal with that at all. And generally, a serverless solution lets you spend less money. Part of the original cloud promise is that you pay for what you use rather than a sort of fixed cost. And the other things about serverless is that they provide you a sort of a simplified programming model. It's just your code that you have to write. You don't have to worry about the drivers and the services and things that run on that machine. It's just your code, and that is it. And executes for you as fast as it can. Now, it also simplifies your DevOps because the serverless apps tend to be smaller. They have less dependencies on other libraries and things, and they can just build and deploy. It's a fairly straightforward story. And like I mentioned before, the consumption billing, it helps you sort of eliminate the problem of over and under provisioning. So what I mean by that is if you go and buy this huge bulky server, it's got 128 gigs of RAM and 64 cores, and you only ever use 4 cores, you're sort of completely over provisioned. You spend all that money on beefy hardware that you just don't need. Same as you have a very demanding application, but you're running it on an i3 processor, for instance, and it just doesn't have enough RAM to hold a single image in memory. So using the consumption billing, you pay for the compute and memory that you use for that period of time. So it's quite nice. And they just provide that for you, and your application runs until it's finished, and that's it. You only pay for that bit of usage. And also, serverless applications, they are event-driven scaling. So depending on the number of requests or the number of messages in a queue, your application can actually scale out to multiple instances as much as it needs to take care of all the events that's coming its way. That's really, really nice. So, and when all that demand has died down, you can scale back down to 0 because there's nothing happening. There's no events coming in, so you don't pay anything. So that's really nice. And again, because the applications are a little bit smaller, and if you do it right, you actually have less coupling between your services, and that makes your applications much easier to test. So you can just pull it out into isolation, test just that bit of functionality, make sure it's okay, and that's it. There's no need for you to spin up a huge galaxy of microservices and have everything running in exactly just the right way just to test one thing. So for me, there's all a lot of good benefits. So what are the services available in Azure for serverless? So for compute, there's Azure Functions and Logic Apps, and also the container instances. So you can, a good choice of how do you want to run your application, or even the sort of low code, no code application for Logic Apps. It's really nice. And if you want to run something that doesn't quite fit into the first 2 categories, you can use the container instances. Then for data, we actually have quite a variety of options. We've got Cosmos DB, SQL also has a serverless offering, and storage accounts. But none of these you actually have to worry about the underlying server or actual hardware. You just say, I want space, I want somewhere to put my information, and that is it. That's all that you have to be concerned about. And that makes life a whole lot easier. Then how about messaging? How do we make our applications talk to each other? So there's a whole bunch of different messaging services, but my top 3 are Service Bus, Event Hubs, and Event Grid. So but for tonight, I'm going to go pick this slice of Azure. So why do I want to pick Azure Functions? Well, for me, the elastic scale is really important. So when my application is not being used, it's at scale 0. There's nothing running, so I don't pay anything. When it gets busy, I'll scale out to however many instances I need, and I'll pay for just that little bit. Now, the nice thing is that the applications can actually run anyway. We have Azure Functions or Functions as a Service. We can run them in Docker, so the Azure Functions runtime can run. You can get the Docker image and run that in Kubernetes, wherever you want, even on-premise, if you really wanted to do that. So that's quite nice. And this is also, for me, a big part of the original cloud promise, like I said, that you pay only for what you use, and there's no fixed cost to using Azure Functions. Then Cosmos DB, for me, the NoSQL model, or the not only SQL model, is really nice. I like the flexible schema. Configuring EF Core and SQL Server and working out all the relationships and everything, wrangling the data to fit that table structure is, it's getting annoying. I like to take my data and write it as is. And the really awesome feature for me on Cosmos DB is the change notification. So if something in my database changes, I can get a notification about that and react to it. And I'll show you how that works later. For Service Bus, sort of the premium messaging service in Azure, is that they guarantee the delivery of messages that go into this bus. Now we can do that with queues, so we can queue up a message, or we can take that message and put it on a topic. And with topics, we get subscriptions and filters, which are really awesome functionalities for filtering out different types of messages that go into the bus and giving that to just the right application. So we don't have to manually, for each application, figure out which messages they can consume. So I'll show you how that works as well shortly as well. So here is our classic application again, right? So we've taken this, and after a bit of tinkering around, we've come up with a serverless solution. So now this is not the full implementation of a blog application. It's just a small slice of what you can do for a blog application. All the complexity of profiles and managing your users, etc. You can still implement that. But for me, what I'm going to show you is how do we deal with resizing images and rendering the markdown, for instance, once new content has been added to the blog, and how do we then sort of take care of the number of likes in our posts, and once there is new content in there, I can run another function that works out the average reading time for that content. So I'm pretty sold on this, right? There's some cool stuff in there. It seems like I have a nice and simple solution, but I can already hear some people asking, how does Solid apply to these serverless applications? So this is where I'm going to start off by going through the principles one by one. So first, the single responsibility principle. It means that application should only have one reason to change. You should have one job. And for instance, if we look at our application here, the resize images function, it should just resize an image. When it gets a message to or a request to do that, it should not go and start printing an image and emailing it off to somewhere else. It should resize it and store it, and that is all it needs to do. So it's got one responsibility. The same applies to our Markdown application. It should do just the one thing. And so for me, if you have all your separate concerns, if you can break them up into small applications, that is a big, big win. You can actually simplify things, make your life a whole lot easier. The next two principles, the open-close principle and the Liskov substitution principle, they go hand in hand. So when we say open for extension, closed for modification, it's sort of like we want to take a class and inherit from it and change the functionality, make it do a little bit more, but we don't want to modify the original class itself. I'll show you how to do that with Azure Functions. Same with the Liskov substitution, is that we want to substitute an implementation with the same functionality. So when the base application is, for instance, to resize images, then one I replace it with should still be to resize images and not send emails, for instance. It's a silly thing to do, but hey, I'm sure stranger things have happened. So here's just a smaller slice of our application where we have our resize images function, and that's at version 1. So we now want to write version 2. It's going to do things a little bit quicker. It might have a higher quality filter, and it might store the images or optimize the file size for us a little bit more. Now we can actually do that in a sort of blue-green deployment scenario where the version 2 is running alongside version 1. The output is pointing towards a test site, and we can monitor any results with App Insights or whatever monitoring tool you choose. And once we're happy with the results, we can then point the output of version 2 to the production site and turn off version 1. There we go. Now version 2 is slotted in place, and we have a nicer, faster application running. That's pretty cool. Then the interface segregation principle. Now, so normally it would say only add the functionality that will be used. But in our case, we're going to talk about endpoints. So only add the endpoints that will be used. A lot of the times people would go, hey, I want to write a serverless application. And they're going to add all the endpoints that they need for their application, for all their concerns into one Azure Function application. Now, That's going to make your application binary size, for instance, just grow. You have a lot of dependencies that you have to load in. When your application starts up, there's a lot of things to inject and prepare and load, get ready, and that's going to have a negative impact on the start time of your application, as well as when it needs to scale out. That same cold start time will apply to new instances being scaled out. So if you have a huge amount of events coming in, a very high load, your application is just going to be able to slowly deal with it rather than very quickly spin up and instantly be able to get through that high demand. So if we look again at our resize images application, because resizing images is a lot more work than rendering Markdown, for instance. If this application, it's decoupled from the Markdown application, if it gets a lot of load and a lot of messages coming from Service Bus, then it can independently scale out from the other parts of our solution and work as hard as it can to get all the images resized and saved to the site. So comparing that with our classic application, if we wanted to resize all the same number of images, either the process would take a whole lot longer to complete, or if we try to just use as much CPU as possible just on resizing images, we won't be able to render Markdown and won't be able to process new requests or upload new content or even serve the content to our users because we just overloaded that poor little server. But in this case, because it can scale independently, just for that feature, that is really, really awesome. So in a nutshell, keep your application small and again, even relating that back to the single responsibility principle is that it should just do one thing, because if that thing needs a lot of power, it can grab as much as it needs. Now, the last one is the dependency inversion principle. And academically, it says code towards the interface. And I struggled with this one for a fair bit because how on earth am I going to apply this to a serverless architecture? And the key word in here is code. So I couldn't really find anything other than now we can do real dependency injection in our serverless application. So I'm going to take that as a win, right? Because for a very long time, we didn't have this capability. The function apps were very simple, and we had to write up a lot of dirty code to sort of try and work towards something that looked like a DI framework. There's a lot of libraries out there that try to deal with it in functions v1 and 2. But now it's built in. It's there for us to use. It's very familiar to what we're used to in ASP.NET, or ASP.NET Core. And it's really, really simple to use. So all we have to do is implement or provide our own version of the function startup class, where we can go and add services to a function host builder. So it's very similar to what we used to. And we can see here, I'm injecting an image resizer. I'm using the Langkot's image resizing implementation. And so when my application receives a message from Service Bus, so we're using that Service Bus trigger, and I'll cover the topics and subscriptions soon. But when we receive that message, I can go and read it, and because all my messages, I sculpt them as mediator requests, I can deserialize that message directly into mediator request and send it through the pipeline. And I can do that by injecting my message reader and mediator itself. So this is nice and simple code. I don't have to new up anything myself. I just take care of all of that in the composition root or that startup class. And then I can just write nice, clean, simple code. And if I ever need to swap my message reader, I can do that quite easily in one place. And I don't have to do it all over the application. So here's just when the image upload message was sent. And again, I can inject my resizer, even a downloader. The reason is you don't want to put a whole image in a Service Bus message. Most likely won't fit. So you have to then, part of that message should say where to obtain the image from. So I'm going to download that image, and then I'll resize it. And obviously, I think there's a line of code missing there that says to save the image, but we'll overlook that mistake for now. But yeah, so you see, nice and simple code. We can inject our interfaces, make them just do their job. It's easy to understand, easy to maintain. Cool. So we can look at the 5 principles, and we can tick off each and every one of them. So now we have the solid principles. We can use them to easily reason about our applications. How do we need to slice them up, and how do we structure a whole application with this and keep it nice and simple and keep everything nice and honest. So we know now clean code, solid principles, and we can apply it to a serverless application or a serverless architecture. But how do we make our applications resilient? Those little flames we saw earlier, how do we take care of them? Now, when we talk about resiliency, the reason is we don't want to lose any operations. A blog site is one thing, but a commercial application is another thing. For instance, if someone clicks the buy button and that message is just not going through, you're missing out on potential revenue. That's bad. And also the experience of not being able to buy the thing you really, really want right now, you might never go back to that site ever again. So we want to be able to capture all of our operations, guarantee that they're going to get processed. And if things do go down, which they do, right, we want to be able to resume and take care of everything as soon as possible. And essentially, we just want to provide a very available or highly available service to our users. So when do we start panicking? Well, a lot of developers will joke and say, hey, the data center caught on fire, some natural disaster happened there. But they're very infrequent, they do happen, but more often it's when someone's accidentally gone and restarted a service, even though there's a confirmation button that says, do you want to restart the service? And people just blindly click OK and then realize, oh, I shouldn't have done that. But that happens. And even when we deploy a new version of the service, we have to take it offline to swap in the new one. And people do that by accident. It happens. And transient errors, the sort of half unexplained errors, or your server is being overloaded, or you're making too many connections to the database and your connection pool is run out and you can't take care of it. But if you wait just a little bit longer, the transient error goes away, everything's back to normal. So we want to try and deal with all of these panic situations. So again, here's our classic blog application. And when things go wrong, we just can't get to anything. We don't know what our users are going to see, and we're starting to panic. So how are we going to solve this? How are we going to add resiliency into our application? One way is to use asynchronous messaging, because HTTP requests, they can time out, and that sucks. You can't recover from that operation. It's essentially just lost. So like I said, click the buy button. If that request doesn't make it to your back end, it's lost. And if your back end received it before writing it or processing it, and something crashes it, for some whatever reason, well, it's lost as well. So it's not great. And the good thing is, though, by using the asynchronous messaging systems like Service Bus or the other ones, is that those messages are persisted, and they can last for a long time, and they should be able to outlast those outage periods as well. And another great benefit is that we'll show you shortly is that by using asynchronous messaging, we can actually decouple our applications from each other. So that dependency or tight coupling, we can get rid of that. So applications can stand on their own, and they don't really need to be concerned about any of the other applications or services around them. Now, we also can follow some high availability patterns, or even some of the services out there to help the scenario. And one of those things is we have to deploy to multiple regions. And I'll show you some really awesome examples to how to do that. Your applications could also internally implement the outbox pattern. So just as an extra safety measure, before sending a message onto the service bus, you can persist that message locally. So you can store it in a queue or a database or even a file if you really had to. As long as you have some sort of record of what you need to send, and once it's sent, you can tick off locally that you've sent it. That's a really great little pattern to follow. It's very popular. It's fairly straightforward to implement. But only add it obviously if you need it. But I think it's a great option to add in most of the time. and retry patterns. So like with I mentioned earlier, the transient errors, if your database is struggling a little bit, for instance, and you're losing connections, if you retry a couple of times, usually things go through. So there's some great libraries that you can use. The retry pattern library like Poly, it's really, really nice. But recently, Azure Functions have actually added a retry policies attributes that you can put on top of your functions to make things work in a different way. And you can apparently also implement your own policies as well. So I don't think that's GA yet, but yeah, keep your eyes on the Azure blogs. They should start showing up pretty soon. Okay, so here's our serverless architecture, our blog application. And like I said, things can go wrong. Now, even though it's serverless, those servers that are somewhere, they can go offline for a little bit. And we can, again, start to panic because things just aren't going through. It's just not happening. So the good thing is, though, we are using messages. So that message that was persisted on the service bus, when this function becomes available again, it can just start listening, consuming messages off that bus, resizing the images, putting them to the side, and yeah, it's all happy days, not a problem. We never actually lost that operation at all. Same with when our Cosmos DB change feed functions, when they come back online, they can look at the change feed and say, hey, there was some content added. I can, in the last 5 minutes or however long I've been down, I can start feeding those documents in, process them. I can count the number of likes or dislikes. I can calculate the reading time, save it back to the database, and it's all fine. Nothing's really been lost. And same for our render markdown function. When it comes back online, it can continue processing. So actually, everything's quite cool. It's all back to green. We had not lost anything. Happy days. And we can stop panicking. So Service Bus sounds awesome, but what can go wrong with Service Bus? It's a service, and services themselves can go down around the world. So if we look at Azure, we've got like 60 plus regions now. It's really cool. They're all over the world. But I'm going to just focus here on our part of the world in Australia. So let's say I'll take my blog application and I deploy that to Australia East, so into the Sydney region. And the Sydney data center goes down, it's not great. So the whole service bus can go down and I can't send messages to the bus and my applications can't react to the messages. It's just standstill, it's off, it's offline. So we're back to square one and that's not great. So what do we do about that? So this is where we want to talk about high availability. So we take our service bus and we deploy 2 instances of it in 2 different regions. You can do more, but I'm just going to focus on 2 for now. And there's an active replication pattern that we can follow. So our application, when it needs to send a message, it actually sends a message to both instances of service bus. But on the receiving end, we have to really be careful because depending on the operation, if we process the same message twice, I'm going to deduct an amount from my bank account twice, even though it's for the one thing. That's bad, right? You don't want to do that. So you have to make sure that the operations that you're sending on this pattern are idempotent, or however you say that word. It's not my favorite English word. Or the other solution is that to make sure that once you receive a message, that you deduplicate them. So you only process one of the 2 messages. So if you already processed one, you don't process the second one. There's a bit of complexity you have to add into your listening applications to be able to deal with this. And if we put that into a picture, this is sort of what it looks like. So we have our sending application. We can see that the messages are going to both active regions, region 1 and region 2. And our listening application, it will receive both of them, but it has to go through that logic to deduplicate the message before it can go and handle it or execute that message. So yeah, not bad. This works, but a little bit of complexity in there. There is a more recommended way. It's the active-passive replication pattern. You don't need to employ to develop the deduplication logic. And and then how we do that is to just send our messages to the active region or the active bus, and only when something goes wrong do we fail over to the passive region. All right. So in a picture like this, our sending application first, it'll try and send to the active region, and the application would read from the active region. And essentially, it'll listen to both at the same time, but a message would only be received from region 1 at any time. And then it can go and just handle it straight away. It doesn't have to deduplicate or figure out anything. It just receives it, handles it. But if, for some reason, the region 1 or Australia East goes down, and that message fails to queue onto service bus, then the application goes and sends it through to the passive region, so the bottom one there. And the same thing is that the application listens to region 2 at the same time, a message comes through and it handles it. So this is the preferred way. It's really nice. But then what about our Azure functions as well? If we deploy them into the same region as our active region 1, and if that data center goes down, our function apps are down as well. So how do we deal with that? So we want to make our Azure functions highly available as well. So just like with the service bus, we can deploy 2 instances of the application into 2 regions. But things are a little bit seemingly backwards. We can go to the active passive pattern. So the sending application sends to the fail one. It sends to the active region first, and only if the active region doesn't work, we fail over to the passive one. But then the listening application, it gets very weird. It's like some really crazy engineering you have to apply to get this working. And it just doesn't sound like a great scenario to be in. Now, the other way around is the active-active way, which is actually recommended. If you go look into the Microsoft documentation, they say that you have to send the same request to 2 applications, but how does that work? It's 2 different applications to do one thing, and again, I'm a little bit confused, but their answer is actually to use Azure Front Door. It's a really cool service from Microsoft, and it helps us to deal with this active-active scenario. So we go and spin up a Azure Front Door. We configure it for 2 regions, and we add our backend APIs into each region. And at the same time, I'm using Cosmos DB. Now, Cosmos DB actually gives me all the high availability that I need. It can deploy the database into multiple regions quite simply. It's just a couple of clicks and you can get that done. And I can also write to the closest master or closest node as well. So compared to, say, a SQL database, you can get the same sort of setup, but generally you only have one write master. So if that's in Sydney and I'm trying to write from Melbourne, it's going to be a little bit slow. Whereas with Cosmos, I can write to Melbourne and I can write to Sydney, and Cosmos takes care of all the replication for me. So that looks pretty cool. So I can actually send a request in through Front Door, and it will then, through its health probes and monitoring and metrics and routing rules that we put in there, it'll then decide which region to route that message through to give us the best sort of response for that request. Now, what about our service bus? We haven't actually put that into the picture yet. So here we go. And we take our service bus active-passive pattern and we combine it with the functions active-active pattern. And it looks a little bit crazy, but if you look at it for a minute, it actually makes a whole lot of sense. When a request gets routed to the Australia Southeast region, we would use the local service bus there and fail over to the one in Sydney. And the converse is true as well. If a message is routed to Australia East, the bottom one, we will use that local service bus, but fail over to the one in Melbourne. So it'll ping pong between the 2 regions for us, and everything just works. And Cosmos DB, it just sings along, does its job. We don't have to worry about anything. So now we have a really highly available Azure Functions application, with a highly available service bus running, and yeah, an awesome database. Everything is pretty much just how we want it. It's really cool. So a few tips with the messages on Service Bus is that you should try and include as much useful information as you can in the base message that you send across. And these are things like the message type. I prefer to include a .NET type, so I can deserialize that into a known contract in my functions, and then I can process them quite confidently. And correlation IDs and timestamps and all that, very useful things that you can use to track the lifetime of a message or an operation through multiple services. And with Azure Functions, we use the Service Bus trigger to listen to a service bus for any incoming messages. And if we need to send anything, we use the topic client. Now, I have an example of how to do all of this on GitHub. It's a workshop called the Magic Bus, Enterprise Bus Workshop. Brendan Richards and I did for NDC Melbourne last year. So if you go there, you can check it out. There's quite a lot of code in there for you to examine, but I'll just show you a small slice here. So I have a service bus message sender. And like I said, we're using the topic client. And in that message, the bus message, I include the .NET type as the label. I make sure that I'm saying how I'm sending some JSON data here. We have to be nice and explicit and honest of what we're sending. And I'm adding a correlation ID. So any message that has come in, if I'm processing or sending off another message, I carry over that correlation ID. I don't go and create a new one, because then now I can't correlate them. You can't put the story back together at all. So that's very important. So we send that with this message bus sender, and on the receiving end, to read that message, like I said, I want to deserialize that into a concrete type, in this case just the message base. I use this little method here, the get message type. So I inspect the JSON payload there for the message type field, from this previous bit of code. That label, message type, that is this bit here. That's what I get out of the payload. So then I know I can actually return the .NET type to deserialize the message that came in from Service Bus. And again, like we're using the Service Bus trigger to listen to a particular topic, and the subscription filter that we're using. So when I read that message, I can get it back as a mediator request, and I can send it on the mediator pipeline and process it. Very straightforward. So in this case, I was sent a markdown uploaded message, and that was the base class is an I request from mediator, and I'm simply just handling that request as normal. So I can use this code. It's nice and easy to maintain. It's very portable as well, so I can actually, if I needed to run that in a different offering like a console app or even a web app itself, it's very easy to move. Nice and simple. Awesome. So now we know how we can actually get our applications to follow the solid principles. We can make them resilient, withstand outages across different regions, and still have people access the site and read all the wonderful articles that we write. But what about the demand? Suddenly we've got the latest and greatest blog post about the retry patterns in Azure Functions, and now everybody wants to read it. How do we make our blog site deal with this heavy load? So we have to now think, we have to plan for what our maximum scale could be. So we have to see, what is available in Azure. So if you look at the consumption plan, you can scale out to a maximum of 200 instances. Now, each instance is a single core, and I think you get 1.75 gigs worth of memory, and you can have 200 of those. So that's quite a lot of power. And Azure can, and you only pay for just those ones that you use. You can also use the premium offering. So these are much more powerful CPUs, but you're limited to 100 instances. But depending on which tier you choose, you can go to the maximum EP3 tier, and I think it's about the equivalent of 800 instances on the consumption plan. It might be even more, but it's a whole lot more than the consumption. So of course it costs more, but if you need it, you can have it. Now, some people would like to use a dedicated app service plan, but you're very limited to only 10 to 20 instances that you can scale out on. But I think people used to use the app service plans to get over the cold start issue that you would get with the consumption plan. Yeah, because when you're starting from a scale of 0 to 1, that bit of time it takes to spin up the application, that cold start. Some applications don't like that, or some customers don't like that. Whereas dedicated app service plan is always ready to go, ready to run, just like the premium plan. You can have that as well. That's what they brought it in for. So yeah, I find less and less reasons to use the dedicated app service plan. But if you do, just realize that you don't get to scale up very much because you're limited by the compute power that app service can give you. If you want to then scale using Kubernetes, the scale that you can achieve is, it depends how many nodes you've got underneath your cluster. If you're using Kita, what metrics you're looking at to scale out. There's a whole lot of complexity in that, but you can definitely do that if you want to. You just need to plan for it and see what you can achieve with Kubernetes. And some tips for scalability, like with the solid principles earlier, keep your apps small, and also keep your operations short. So as soon as you receive a request, turn it into a service bus message straight away. Don't try and block for a long time on receiving a request. In my mind, as soon as you receive a request, don't try and return a result straight away. Don't block. Return a payload that would say, hey, like a 202 accepted. You can check back for the result at this endpoint, or you can use something like Signal R. So you can have that bi-directional communication back to the client application and push a notification to say when the operation has actually completed. So yeah, keep them short and simple, and it'll let your applications react a lot quicker and help with scaling out as well. Now, when you deploy your storage application, your Azure function applications, generally you have to use a storage account. So they're used for the logs and some state tracking for that Azure function app. Now, if you're intending on writing images and PDFs and all sorts of content to your storage account, I would say to use a separate one. You don't want to be writing tons and tons of information to a storage account, which the Azure function itself relies on for maintaining its state and keeping its logs. So storage is cheap these days, so why not? Use a second one. It'll have a small extra benefit to doing that. And yeah, so like I said, one function for the triggers and bindings. Keep them small, and yeah, nice and simple. You can also go and make use of the Azure durable functions. You get a little extra oomph out of your applications. Now, I'm just going to call it one of the patterns, which is the fan out, fan in pattern. Some people also call it the MapReduce pattern. So if you get a request or an operation that comes into your application, if it's a workflow that you can, instead of many steps, one after another, you can do them in parallel, for instance. If it's you need to render the images and calculate the reading time and render the markdown, you can do all of that at once in parallel. So you can fan out, you can run those activities all at the same time and collect the results at the end there and produce a final payload or result to the calling application. So that's nice and simple. They've taken away a lot of headaches to make this work for us, and you can scale out and you can run this on the Azure Premium functions instances as well, and it's really awesome. Right. So, like I said earlier, turn your requests into messages as soon as you can, and when you're using Service Bus, try to use the topics. Because if you're using a queue, it only allows for a single listener or a single consumer out of that queue, which, for some applications, that's totally fine, not a problem. But when you want to sort of go and publish a message, fire and forget, and want to have one or more applications react to it, you have to use a topic. And that way you can have multiple listeners to the application, to the service bus. And you can, again, fire a message out. One message can then spark off 3 or 4, as many Azure Function apps that you need to run that function in, or run that message and process it in parallel. So it's a nice way of scaling out your work. And then here, like I said, to use topics. Inside of when you publish a message onto the service bus, onto a topic, you can call it the blog topic, for instance. And inside of the Azure Function application, you then connect to a subscription. Now that subscription has the SQL filters. There's other types of filters as well. But this is where you can say that this application only wants to listen to the blog content updated message or the render markdown uploaded message. You can write all sorts of filters to so that your applications can only pull or receive messages that they understand or what they're only interested in. If there's 10 types of messages and it only needs 2, you can write a filter to make that happen. It's nice and simple, and it's even in terms of a DevOps story, it's fairly straightforward to set this up and provision it out to your environments. Finally, then with your scalability is when you need to write data, always try and choose a very high throughput storage mechanism. So my favorite, Cosmos DB, but it's not appropriate for everything. Even so Event Hub as well. If you want to send up a whole lot of other messages, you can do that. Or for storing files, premium storage. If you want to get data out of your application as fast as possible, choose the best medium possible. And also, when you want to try and limit the connections that you make to your storage accounts or storage services. So when you inject them or spin up in your application, generally the recommendation is to use them as singletons. As long as your clients that you're using, so the Blob client or the Cosmos client, they take care of that connection pooling for you. It's not really something you want to implement yourself. But you don't want to be running out of connections by accident. By creating a new connection on each request. You want to be able to reuse them and recycle those as they become available and never really have to deal with those transient issues. Awesome. So now to wrap it up, we looked at clean code and solid principles, how we apply it to a serverless architecture. We know how to have very, very resilient applications. They're not brittle. They don't just crumble when a small thing goes wrong. And if we get a high demand in our application, we can scale out really quickly. We've got all the tips there. So to wrap it up, use serverless over the traditional approach. It is really, really awesome. You can have a lot of benefits out of it and make use of the cloud in a proper way. So you only pay for what you use, which is, for me, is very important. And solid, it does make your serverless architectures a lot cleaner and very simple to understand. And asynchronous messaging, prefer that over HTTP requests because you get resiliency. Your scalability goes up and it decreases coupling on your services. So it's your whole system is a lot easier to understand. And serverless high availability is super easy. So now you can all go and build rock solid serverless applications. Thank you.